Suppose a magnetized needle or a bar magnet which has a north and a south pole is suspended in a uniform magnetic field of strength B, right? Then we can also determine the dipole of this particular needle, right? And the way to do that is, let's assume that the needle is suspended in a uniform magnetic field of strength B. Now let small m, let it represent the magnetic moment of the needle or the bar magnet. And let it also make an angle theta with the direction of the magnetic field. Now, whenever a bar magnet or a magnetized needle is suspended in a uniform magnetic field, you should realize that it does not, in effect, feel a force, rather it feels a torque. The reason being, at this end, which is the north pole of the needle or the bar magnet, you have a force characterized by the product of the magnetic field and the magnetic moment, which is acting in this direction. Whereas at the south pole, you have the same force given by the product of the magnetic moment and the magnetic field, but it's acting in the direction which is opposite to the magnetic field. Now these two equal but opposite forces, they end up generating a torque which tends to turn this particular bar magnet or needle in the clockwise direction. So they tend to rotate this in a clockwise direction till eventually the north pole faces this end and south pole faces this end. And that would become a stable position for this particular bar magnet or needle. Right? So every time I am trying to turn this needle away from the stable position, I am doing some work. And I am doing that work against this uniform magnetic field. And that work gets stored as potential energy, a concept that we'll study a little later. But now, if I were to determine the torque that's acting here, so let me characterize the torque that is being generated. So this torque is a restoring torque. Restoring torque, we call it restoring torque because it always tries to bring this needle or the bar magnet to the stable position. It tries to restore stability. Hence it's called the restoring torque. Now this restoring torque, let me characterize as tau. Now tau is given by m dot b. Again, you should remember that the magnetic field is again a vector. The magnetic moment, the product of these two, which is a cross product, can be characterized as m dot b into the perpendicular distance between these two equal and opposite forces, which is nothing but the length of this bar magnet, right? So that I can characterize it as being given by sine theta, because the angle that this length of the bar magnet makes with the magnetic field is theta, and if I drop a perpendicular here, this length is given by sine theta. This perpendicular distance between these two forces is given by sine theta into this length, and that length anyway gets taken in by the magnetic moment. Now, if I were to take this discussion a little further, you'll realize that d square theta by dt square into I. So where I, let me again define I is the moment of inertia. So moment of inertia into d square theta by dt square should be equal to the restoring torque. But since these two act in opposite directions, this is the work being done, which is the opposing torque, whereas this is the restoring torque. Since the two are in opposite directions, we take it with a negative sign. Now, what is this d square theta by dt square? It is the double differentiation of the angular distance with respect to time, right? So when you do a double differentiation of the angular distance with respect to time, you get angular acceleration. So this can also be written as I alpha equals minus mb sine theta, right? But I'll continue with this. Now, if I keep this term on one side and take I to the other side, I'm left with mb by I sine theta. Now, the angle of deflection here, theta, is considered to be very, very small. Hence, at small angles, theta is equal to sine theta. Hence, we replace sine theta with theta. What I get is d square theta by dt square equals minus mb by I theta. Now, if you just look at this right side of this equation, I can rewrite this as omega square theta, d square theta by dt square, which is my alpha or angular acceleration, is equal to omega square theta. So what does this remind you of? It is a case of simple harmonic motion. So it's a case of simple harmonic motion, which I can then state as where omega square is nothing but my mb by I. So this is a case of simple harmonic motion. So you've already studied simple harmonic motion last year. So any motion that's repetitive, right, becomes a case for simple harmonic motion. Now I also know that time period is given by 2 pi radians by omega. So if I substitute this value, so this I can, if I take the square root on both sides, this becomes square root of mb by I. So if I substitute this over here, I get t is equal to 2 pi divided by square root of mb by I, or I can rewrite it as 2 pi square root of I by mb. So this is how the time period is linked with the moment of inertia, the magnetic moment, and the magnetic field. When you place a magnetized needle in a uniform magnetic field, redo is try to isolate magnetic field on one side. So I'm left with T square equals 4 pi square. If I take square on both sides, if I square both the sides, I'm left with I by mb. So if I take b on one side, I get 4 pi square I by m t square. So this is a very elegant way to calculate the strength of a magnetic field by placing a magnetic needle or a bar magnet with whose magnetic moment and moment of inertia are known beforehand. So using a dipole, we can use this concept to arrive at the magnetic field, or we can also use this equation to calculate the magnetic moment of a bar magnet by placing it in a field of known strength. So both these possibilities arise because of this particular relationship.